I'm extremely pleased tonight to introduce our speaker. Dr. Ann Gaffney from Arco Chemical Company is now manager of Catalyst Research and Development at Arco. Dr. Gaffney got a bachelor's degree from Mount Holyoke College and her PhD from Delaware University in 1981. In her work at Arco Chemical, she's been involved in quite a large number of extremely interesting and very timely topics of catalysis. Among those, she was one of the original workers in methane conversion. And for those of you who are not knowledgeable in this area, Arco has a commercially proven methane conversion catalyst. Dr. Gaffney is also interested in catalytic cracking, hydroformylation, selective oxidation, and homogeneous catalysis. I think it's fair to say Dr. Gaffney is one of the experts in the area, and we are extremely fortunate to have her speak to us tonight. Her topic tonight will be Superflex, catalytic conversion of refinery streams with oxygenated fuel production, which is an extremely timely topic. Dr. Gaffney.
Okay. Well, thank you so much for the opportunity to be here. I did visit your organization back in 1987, and it was a great experience, and I'm glad to be here again. And we'll hop right into the talk. As Fred mentioned, it's a very timely project because, as you know today, there's a great demand to put oxygenates into our fuels. It's being government regulated at this point. And Arco is a worldwide leader in producing MTBE. We hold at least 30% of the market share worldwide. And actually, it falls out of our technology for producing propylene oxide. This project started in 1988, and our driving force was really to find a cheap source of propylene, because our company makes propylene oxide, and we need propylene as a feedstock. So that's how the project evolved. And today you'll be hearing about the what we've done basically to do catalytic cracking of hydrocarbon sources to make light olefins. Then you'll hear some talk and discussion on isomerization of normal olefins to isoolefins in order to make the ethers. Just to give you an idea of what other ways you can make light olefins, well, there's conventional steam cracking that's been around for ages, but that favors actually ethylene as a primary product. Then, of course, you have FCC type technology, where you're producing quite a bit of gasoline and heavier materials. Then you can look at the Oleflex technology, typical of UOP, the dehydrogenation of alkanes. Then, of course, there's a metathesis chemistry, taking a C4 and C2 olefin and making a C3. And what you'll be hearing today is cracking of paraffins and olefins and mixtures thereof, which we've given a trademark of Superflex, that's what we call it. And this work actually favors propylene and butylenes. And you get a very high ratio of propylene with respect to ethylene. And as I mentioned earlier, you're able to skeletally isomerize the normal olefins to the branch to make tane and MTBE. From a scale-up point of view, it's simplified because it's very analogous to FCC technology, which is really to our advantage. And a comparison, we have Superflex versus FCC, and we form very little coke, less than 1% typically. Our temperatures are a little bit higher in the riser. Regeneration temperatures are nearly equivalent. Our feed is lighter. We're looking at C4s to C10s, whereas here generally your C12 is higher. and we're at a higher or lower cat oil weight ratio. But if you do it on a mole basis, they're fairly comparable, and it has a competitive catalyst makeup rate. So things were looking fairly good from a scale-up point of view. So what are the advantages of our technology? Well, it's an alternate route, obviously, to the light olefins. Another nice thing is you can integrate it into an olefins plant or a refinery, and that's, from an economic standpoint, that's the best way to do this. Recently, Chem Systems did a economic review of the Superflex process, and it published in October, and they gave it very favorable rates on an economic basis. You're able to upgrade low-value streams to light olefins, and you get primarily your C3s and 4s, the high ratio that I mentioned. You can get your isobutylenes and isolanilines, and the capital is quite low. So in order to implement this, it would be an relatively easy process in terms of putting it into a refinery or an olefins plant. We've demonstrated a lot of different feedstocks. We looked at different olefin plant streams, refinery streams, and also the pure component systems. And most of the work in research we did initially on pure components, mostly normal butylenes, in order to get an understanding of the chemistry and to develop the catalyst. But then, as we progressed, we actually ran all these different feedstocks in a pilot unit. And in one case, we ran the pilot unit for 3 months in order to really demonstrate the technology. And some of the work you'll hear about today is a VTX raffinate. We call it a UDEX raffinate. So you'll be seeing data on that also. As far as the thermodynamics, if you look at the olefin equilibrium for C2 to C6, just the olefin equilibrium with respect to temperature, well, steam cracking, you're generally up around here, 750, and you're favoring the ethylene versus propylene. Whereas our technology, we're operating around 600, so equilibrium, you're favoring propylene versus the ethylene. Then again, the FCC technology that we talked about earlier, you get a higher product slate towards the heavier materials. So it's sort of a nice niche for our, in terms of thermodynamics, for taking advantage of that window in order to favor propylene. As far as what do we need to achieve commercial catalyst requirements? Well, we had to have sufficient activity, obviously, and we wanted to run it in a fluid bed reactor, so we had to reach equilibrium quickly in a matter of seconds. And of course, we wanted to minimize what we didn't want to make, aromatics and paraffins. And since it wasn't a fluid unit, we kept our attrition quite low. Our target was less than 15, but a lot of our catalysts were quite low, much lower than that. And of course, hydrothermal stability was important because you're burning off a little bit of coke. And as you see later, the process works a lot better if you have steam present. So we were very aware of that problem. And CSM5 turned out to be the really best component for our catalyst. And we had to be able to produce the final version of the catalyst in a suitable form, spray dried form with appropriate particle size. As far as a very simple idea of what the catalyst working environment is, this is representative of our pilot unit, and most of the chemistry, of course, is operating in the riser, and the riser temperature were 550 to 650 degrees centigrade. Very short residence times, 2 to 6 seconds. And you can put steam in there, or you can minimize it. The amount of steam is very variable here. And then what happens is you have the catalyst and the products go to a stripper, and your catalyst comes back down and over to the regenerator to be regenerated, and your products are separated out in the quench tower. So basically all your temperatures are running around 550 to 650 degrees centigrade. and the stripper and the regenerator do have steam up to significant amounts of roughly 5 to 50%. But in the very beginning of the project, we were looking for catalytic materials, and we focused on various zeolitic materials, and we found ZSM5 to really be the best in terms of activity and selectivity. And other things that we looked at were ZSM11, beta, Y, mordenite, USY, ZSM34, omega, and we even looked at non-zeolitic material. A little bit hard to read, but basically the two top data are two different ZSM5 preps. Very similar, you get very similar data. You're at a weight hourly of 833, which is the highest weight hourly in this chart, and as you work down the chart, your weight hourly is falling off to 7 and 4. So you can see a decrease in activity as you change your zeolitic material. The last two are actually non-zeolitic. The entry here is a matrix, which was used to formulate the catalyst. And at a weight hourly of 7, you're only getting 9% conversion. So that gives you an idea of the spectrum of activity that was obtained with various materials. The best selectivity was with ZSM5, and nothing really compared to it. So we focused a lot of our attention on ZSM5. And so initially we did synthesize and characterize and evaluate many materials, but then ZSM5 was the one in terms of activity selectivity. And there was some work looking at different silica-alumina ratios, and the best compromise appeared to be around a ratio of 40. And we found that we really didn't need a very specific crystallite size, or it didn't even have to be an expensive template prep. You could incorporate phosphorus into the ZSM5, and we found that this brought on nice properties of hydrothermal stability and increased activity. And that solved a lot of problems for us. Phosphorus, we looked at many different loading levels and ways of incorporating it in. And really you don't need too much to optimize its properties. And addition of steam into the feed actually enhances all these results. As far as what we think the mechanism might be, if we're running with butenes, we think it's a simple bimolecular reaction, so that you initially couple and form a C8 olefin, and that will disproportionate by various groups eventually to give you C3, C2, C5, or another route could give you aromatics. Some early data that was generated by one of our research people. From that, you can actually get somewhat of a second-order plot. You're looking at various contact times, and then this expression comes from a second-order rate law, which I'll show you. But it seems to obey that rate law fairly well. Out here, the contact time is so long, you're really at equilibrium, so we're not really considering this data point here. And this is with a ZSM5 catalyst. To show you from that data what the reaction scheme is. It's basically a bimolecular reaction, and you get this expression. This is what was plotted on the y-axis. So the rate constant is extremely high, much greater than 1. And we were interested in where is the catalysis occurring? Is it occurring on the surface and at the pore mouth? Or is it actually, is there some diffusion into the pore channels? And is it occurring within the structure? Well, some data in the literature indicates that diffusion into ZSM5 at these temperatures with molecules of this size is extremely low and much less than 1 square centimeters per second. So I think we're looking at two different regimes, and we felt fairly confident most of the catalysis was at the surface and the pore mouth. And as far as phosphorus and steam and what effect that may have, well, if you put phosphorus on a ZSM5 catalyst and then hydrothermally treat it, your activity goes up fourfold. It goes up fourfold. Whereas if you don't put any phosphorus on the ZSM5 and then steam it, your activity decreases twofold. So there's definitely an advantage there. And you can't avoid the presence of steam because you will have it present in the regenerator, the stripper, and during when you're removing coke. As far as the data here, we're looking at pretty much what was just mentioned, with phosphorus prior to steaming, then after steaming. So your weight hourly is going up by a factor of 4, 31 to 125. Here you have the straight ZSM5 with no phosphorus, and after hydrothermal activation, so-called activation. And to get the same conversion, you actually decrease your weight hourly in half. As far as conversion over this phosphorus modified ZSM5, this is what we focused on. It was working well. We looked at butene, normal, octane, and that Udex raffinate that I mentioned earlier. This bar graph over here shows the conversion, so you can see that the lighter butenes crack more readily. You're at a much higher weight hourly of 125, and you're achieving conversions above 60. Whereas the other feeds are, it's much more difficult to convert them. But on doing so, you can see that the selectivity in all cases favors the lighter olefins, primarily propylene, ethylene, and butylene, and some C5 olefins. Very little coke. So just to reiterate, we thought we had a commercially viable catalyst. Had good activity, increased with steam. We found out to maintain high activity, it's good to expose the catalyst to steam as you're running, either continuously or intermittently. And prior to getting the catalyst on stream, we found that you had to do a severe steam activation step, and you'll be seeing data to that effect. You can have, that steam activation step is rather rigorous, so we thought 1100 degrees Fahrenheit, 1 to 2 atmospheres for 1 or 2 days. But after that, once you're running your process, all you need to do is to add about 0.02 to 1 atmospheres into your system to maintain that activity. And this data came from our pilot plant unit using 2 butene feed. When you're with a fresh catalyst, no steam activation, your conversion is quite low, 25% at a weight hourly of 46. But then upon steam activation, you'll see that your activity goes up to 68, and you're at a higher weight hourly. And some of the better data occurs when you're running with steam in with your feed at some of the higher pressures. And here you're at a weight hourly of 139, 65% conversion. Well, we tried to understand something about the ZSM5, and the starting point was to do magic 8 angle spinning NMR, silicon aluminum. And here we found that silicon is in a highly siliceous environment, very typical of ZSM5. Whereas aluminum initially is tetrahedrally coordinated, no big surprise there, and then of course when you steam it, it's dealuminizing. So we saw very much the typical signals where the aluminum takes on an octahedral environment. Here, this is prior to steaming, and there you have your tetrahedrally coordinated aluminum. After steaming, we see some octahedral aluminum signal for that. Silicon, you have a very typical signal for ZSM5. And with steaming, you start getting the fine structure because you're pulling the aluminum out of the framework, and you don't have the quadrupolar influence on the silicon, so it sharpens up. Okay, well, what happens when you put phosphorus into the ZSM5? Well, first I should tell you the way we introduce phosphorus. We have the ZSM5 initially, and then we do a simple impregnation of phosphoric acid onto the catalyst and calcine it. Okay, so the data indicates or suggests that phosphorus binds to the framework. It doesn't really become incorporated into it. And also we see some de-illumination occurring. And when we severely steam it, the phosphorus appears to remain bonded to the framework through the oxygen-silicon bond. And even further de-illumination is evident. Silicon remains where it is, similar to what you've seen previously. But then once you undergo the steaming program, it appears the catalyst doesn't change with time, so you don't really see any further de-illumination. And but that's in line, I think, with the data that we're seeing. So, again, fresh, this is aluminum NMR, this is tetrahedral, octahedral. Then after severely steaming, you see more octahedral and some non-framework tetrahedral aluminum. So we can't deny that that's happening, but we think that after you severely steamed it, it's stabilizing. The phosphorus NMR, here's the signal at negative 44 roughly, and that is indicative, we think, of phosphorus binding to the framework of the zeolite. This here, the signal at minus 32, is the aluminum phosphate that formed. Then you have the ortho and the pyrophosphoric acid. With steaming, you remove the excess phosphorus from the zeolite, so the signal for the ortho and the pyrophosphate go down, but the aluminum phosphate remains, and also the phosphorus binding to the zeolite remains. Well, we really don't know what the mechanism is, but reading the literature over, and this has been known for at least, I would say, 17 years. Really, the chemists and scientists at Mobile were the first ones to find the importance of phosphorus in ZSM5 and adding hydrothermal stability. And then there were a lot of papers in the literature, and it seems that the consistent proposal that they're showing is perhaps the one shown here, and that the trend in all the papers that I've read is they're saying that the phosphorus converts strong bronze dead acid sites into weak ones, and a mechanism similar to this one may be occurring where it's interacting with a bronze dead acid site. You're eliminating water here, and it can go even a step further to eliminate a second molecule of water. And this would account for de-illumination perhaps, and also allow for the ability to form aluminum phosphate. Also, we notice that some of the data you see later on, it appears that the phosphorus is changing the pore size and also making the path of hydrocarbons more tortuous. So it's actually taking up volume within the pores. So we ran a series of constraint index experiments, and the data suggests that phosphorus may be blocking the channels, and that most of the catalysis that we're doing could be occurring at the surface in the core mount. And there's been some work done in the literature. It's been reported that by high-resolution electron microscopy, that this data also suggests similar findings. So normally ZSM5 would have an index code around 10 or greater than 10. And generally, zeolites that have an index less than 2 are wide pore mouth, and they don't discriminate between a linear versus branch hydrocarbon. And that's pretty much the type of data that we're getting here. So that's why we reached the earlier conclusion I stated. But we still wanted to do a little bit more mechanistic work, so we prepared a modified sodium ZSM5. And where the external sites are propionated, the internal sites were cationic. And then we carried out coking studies with this modified zeolite versus ZSM5. And then we characterized the coke on these materials by xenon NMR. And we found that the modified zeolite, and we also use these zeolites in various catalysis reactions, cracking and methanol conversion. Again, we were using this as a mechanistic tool to understand our Superflex project a little better. As far as making the modified zeolite, you take the sodium ZSM5 that you synthesize, and then you treat it with a very sterically hindered amine so that you're protonating externally and at the pore mouth and very little on the external sites. And we use very highly hindered salts. Examples would be the triambutyl, C4, C5 branched amine salts, basically. From our coking studies, we would generate different weight percent of coke and then do the xenon NMR work. And basically what we're seeing by the NMR studies, that coke pretty much was on the external surfaces. And xenon's a good probe molecule because it can tell you where the coke is and how it's closing off the pore mouth and how much is being formed inside the channel. And so basically we knew we had prepared a material that would be helpful for determining diffusion limited with reactivity. Whereas the protonated version of ZSM5 coke was definitely throughout both the surface, the intersections, and the channels. I don't really have all the data to show you this. We did publish this in the Journal of Catalysis, so I can give you that reference later. But this is just a model here. This is a modified version, lightly coked versus severely coked. Whereas here you have a normal ZSM5 and lightly coked and highly coked. Very simplistic drawing. As far as the catalytic activity and methanol conversion, the protonated version appeared to be much more active than the sodium version. Because under those conditions you are really utilizing the internal catalytic sites. Whereas now we're looking back at the Superflex reactions with 2-butene and octane as the models. We're at such high space velocities that really we saw very similar catalytic activity because we aren't utilizing all the activity inside the pores. And just to show you the 2-butene conversion, protonated versus modified, similar conditions, your conversions are nearly equivalent, and your selectivities are fairly similar. And then we did a constraint index experiment on the modified CSM5 and obtained a low number. And this is in line with the experiment you saw earlier, where really you're not discriminating between linear and branched feeds. And to show you the paraffin cracking, this is for normal octane. And again, at the same conditions, you have nearly equivalent conversions for both the modified versus protonated zeolite. So it seems rather fascinating that here we are using a CSM5, yet really we're only using the surface and the pore mouth, and there aren't really any examples out there in the open literature or patent literature where people have used CSM5 this way. I'll skip over the methanol conversion, but basically you're seeing half the activity in methanol conversion for the sodium modified. So what are our mechanistic conclusions? Well, we feel that our modified zeolite was prepared the way we wanted it to be. In other words, we had activity protonation externally and cations were internal. And this was borne out by our coking study with Zena and Amar. Whereas the HCSM5 version, we're definitely depositing in coke on the surface of intersections and channels. Those are the sites that are being used. And it appeared to be a successful mechanistic tool in our case to get a better handle on the reactivity in Superflex, and that really we're looking at a reaction that's diffusion limited. In order to do the Superflex chemistry, we run at very high space velocities and very high temperatures. And again, we're going into a niche where I think a lot of people in industry and academia really haven't utilized. And it's very good in terms of making light olefins by running under these conditions. And as some of the data that you've seen already, we feel that we're running under diffusional limiting conditions, and that the majority of the chemistry is occurring at the pore mouth and surface. And that's where the catalytic sites are for our reactions. And adding phosphorus to the ZSM5 does give us hydrothermal stability that we need. And as I mentioned, with steam activation, you get higher catalytic activity. Well, we did a lot of work here in 2 years' time. We ran a pilot unit here. It was a significant effort in our research R&D group. We felt that we pretty much simulated commercial operations, confirmed catalyst life, and we were able to prove that you could recycle your materials, which is important. And it demonstrated operation with catalysts produced on a commercial scale. So we had pretty much a process that was proven out in development with many different feedstocks. We had a catalyst that was scaled up and could be, it was easily commercial. And actually right now this technology rests with our licensing department, and we're trying to find a fit for a company who would be interested in making cheap propylene and butylenes. Because that truly isn't our business. We're more interested in propylene oxide. As far as the Superflex catalyst life, as I mentioned, we did run out for here shown 60 days, and it appears to be leveling out around 50% conversion, and the makeup rate is 0.58% per day. So the engineers were fairly happy with those results. Okay, well, once you get your Superflex going on, you're going to get a lot of normal, well, you get butylenes, and the butylenes are under equilibrium distribution, but it would be nice to take advantage of all the butylenes and try to optimize your isobutylene yield. And our objective was to integrate it with Superflex, so we'd have one unit doing so-called Superflex, another unit that could do skeletal isomerization, and that would allow you to make more MTBE. So we worked rigorously here, and we ran the pilot unit, and we were able to get yields of 15% or greater, meeting all the other criterion that you need in order to commercialize this. And in addition to and this was with a Superflex catalyst, so we could do 2 different types of chemistry, the catalytic cracking plus the skeletal isomerization. But at the same time, we discovered 2 other catalyst systems, and they gave you higher yields, 24% or higher, and again met many of the targets that you're looking for. One came very close, another one we're still working on. But just to give you some idea what skeletal isom data looks like, we have 2 Superflex catalysts shown here. The one that ran in the pilot unit, we're getting 50% yield. In the lab, we're getting a little bit higher yield, 19%. So we spent a lot of time trying to figure out why is it we get higher yield in one reactor versus the other, and you'll be seeing data to help explain that. But overall, things look good. I mean, the light's good, it's fluid, attrition's low, it's less than that 15% target that I mentioned. You're at a very high weight hourly. Here showing data at 250. And actually, this other catalyst B was even higher, at about 700. Then another interesting finding, which is totally offline with CSM5. These are all CSM5-based material. So this one is a different zeolite. It's McGapso 31. The composition of matter is patented by UOP, so they have that patent. But we were able to find a niche where they hadn't patented this process under these type of reaction schemes. And so this patent issued very recently to ARCO. But the thing is, it's very inactive. You're at a weight hourly of 46, so you really wouldn't be able to use it in a fluid bed reactor. You'd have to go to a fixed bed. So the activity is low. You don't really have to worry about attrition now, really. And we don't know the life. The life may be an issue, because there is some speculation that effective steam can have some negative impact on metal absos. But it was interesting to find that. Okay, so we tried to understand why is it the reactor in the lab works better than the one in the pilot unit in terms of generating yield of isobutylene. And here are factors shown here: resonance time, pressure, and linear velocities. And they're listed in order of importance. And actually, isomerization is favored by shorter resonance times. In our lab unit, it was shorter, 0.3 versus 1.3. And lower pressures favors this chemistry. And we were at a lower pressure. But it's true that higher velocities are favored by isomerization. And the pilot plant was higher, but as I mentioned, that's a less significant factor. So we thought we had explained some of these differences in our reactor system. So higher temperature favors isomerization versus cracking. And I guess rationale here, it seems kind of contrary to your reasoning, but we thought that cracking needs a longer surface time because it's a bimolecular process. Steam favors cracking. Steam generates more bonds at acid sites for cracking, whereas we felt that the Lewis acidity was more important for isom. Okay, as I mentioned earlier, we thought that the cracking process was actually a bimolecular process, so that would explain the pressure effect. And whereas the isomerization is unimolecular. And as I mentioned earlier, the Superflex catalyst is ZSM5 based. The McGapso is less, this catalyst ZSM5 related, it's less selective because it does crack. You do get propylene and ethylene, and you're going to have to go back and modify it somehow to use opposite. The McGapso is more selective than that, because it doesn't have that extra higher acidity. And here's some interesting data to show the effect on velocity. What was done here is that you have plotted conversion versus selectivity to solid dots or isobutylene. And what we did is we kept the weight of the catalyst constant in terms of volume, but we varied the amount of CSM5 in there by adding a diluent, a very inactive substance, as I showed earlier, alumina. So as you're adding more zeolite into the material, in order to keep the conversion higher, you have to run at a higher space velocity. And on doing so, you favor more isobutylene, and the selectivity to propylene drops off. So that's in line with the higher velocities that I mentioned earlier. So from a conceptual standpoint, where isobutylene selectivity increases with gas velocity, and we feel it's a mass transfer phenomenon, and that really you want both gas to diffuse onto the surface, undergo the skeletal isomerization, and go back out, and not to oligomerize and then undergo cracking. And as far as at a given particle Reynolds number, the mass transfer rate is higher in the treat bed than the dilute bed. So again, we're trying to rationalize the differences in the data, and that helped us to understand the chemistry a little bit more. As far as where do we think we are right now, well, we have a Superflex catalyst that can do skeletal isomerization. It's inexpensive, it's available, it's active, has no attrition. If it has any drawbacks, it's due to too much acidity leading to cracking. And then the other catalyst that you're seeing today is a metal apso, and basically its problem is it's not active enough. Plus, it's much more expensive. All right, well, the other niche there is to do tame. And we did a little bit of work here. It would be good to go back and do more work. I think there's a lot to contribute in this area. And ARCA was able to get a process scheme in terms of doing the skeletal isom on the C5 olefins to get the 2-methyl-butene and obviously make tame out of those, or tertiary amyl alcohol. And there's an awful lot of olefins out there in the United States refineries that we can take advantage of. And if you look at the equilibrium data charts for the C5 olefins, that the mole fraction exceeds 0.8 at 300 degrees F, which is the temperature you might be able to do some catalysis at. So it's really something to go after. And again, our initial work was focusing on the SAPO 11, SAPO 31, and substituting in and looking at various metals. And here you see magnesium again, iron could be interesting, and manganese could be interesting. There's a number of possibilities that you can look at. And of course you can use the Superflex catalyst. It would work also. And so this work started in 1988, and from it we had a lot of success, I think. There were a number of patents that have issued since. They're all process patents with the objective to make light olefins. And you have ethylene, propylene, mixtures of olefins. Some of the zeolitic material that we were fooling around with, we got those patents out. We have a skeletal isomerization patent, purification process patent out there. So we feel fairly confident that we have a technology package to offer to people. And this one publication will discuss the xenon NMR work that I referred to earlier. This is truly a group effort, and these people really make things happen. It was half divided by chemists and chemical engineers, and I think that type of teamwork really helped us move along quickly. And a lot of these names you may recognize from methane conversion. John Sofreco was our project leader and really helped keep things rolling. Andy Jones was the chemist who first realized the significance of ZSM5 and its ability to do this chemistry in this regime. And the other people here, Glenn Cazone generated all the pilot plant data, and Dave Blation, Mark Lipa, and Jack Jubin were engineers that helped to move this along for us. So I'll end it there and handle questions if you have any. Thank you.
They're back to individual. Every bay has a blank.
Yep. Well, we'll open the floor for questions for Dr. Gaffney now. If someone would like to start it up.
Why wasn't CSM5? One strong acid side slide there, why not try something like that? See, aluminum.
Activated alumina, or?
Why don't you use that?
Right. Right. Well, I didn't show that data, but we did look at all sorts of silica aluminas, and basically we did not get the activity that we needed. And I don't really understand what is so special about ZSM5, but it seemed to be very unique for us.
Another question I have is, did you try making, say, vaccine or vaccine other higher outcomes? You try optimizing?
Isomerizing other olefins. No, the only olefin we looked at Feelings and C5 olefins, but it should work for the others. I don't see any problem with that.
Again, I think he's asking, did you try to oligomerize the C4s to C8s, etc.?
Oh, that's very, yes. Early on, when we beginning the process, we did oligomerize it, and you can make it very favorable to C8s easily. There's no problem there. What you want to do is run at a lower temperature and a lower weight hourly.
You said your temperature was 650 or above, 650, 750.
600.
Low catalyst oil, rather low coke make, large steam load. How do you get the heat into this process if you're using a riser cracker type configuration?
I don't know that answer,
words,
but yeah.
The riser cracker uses the calcination of that catalyst and the incipient heat in that catalyst to heat that feedstock.
Right.
And you're running at everything that's the opposite that kind of
You would have to
configuration
supply.
for that.
That's a good
Curious
point.
about the energy balance around.
So like a cat cracker's not balanced?
I don't see how it could be.
Okay,
Yeah, you would have to
what
supply
process
heat
you have.
because your coke weight percent is so low, and you know the reaction doesn't generate heat. So you're right. But I don't know what that number is. It's a good question.
Number of your data, you showed temperatures lower
Than the process temperature. 625, 725 was your range for the process. A lot of your data was 550.
Some of it was 600 and 650. The earlier data, we initially were doing work at 550. And then as time evolved, we were finding, you know, well, really you want to run a little bit higher. And that's actually more optimal.
You didn't go into the methanol to gasoline, but do you get the same products on sodium where it's only on the surface as you do if it's fully exchanged?
Right. We have data showing that at 2 different weight hourlies. Actually, there you're seeing the sodium modified zeolite. It's less active because we're at a lower weight hourly regime. So we feel we have fewer catalytic sites to utilize. So that, I think, helped confirm our thinking in terms of the diffusional limitations and our superflex chemistry.
How do you explain the importance of the long pre-treatment step or activation step while you're steaming for such a long time?
Right. It may very well be that one equation that I was suggesting, that perhaps the phosphoric acid has to interact at the Bronsted site to generate that phosphorus oxygen silicon type bonding. Maybe it has to be rigorously treated that way. But I don't really know the true mechanism.
I take it years ago, ARCO had a tremendous problem getting rid of all their T-butyl alcohol. Now that the tables have turned completely.
Definitely. It's a nice niche to be in. I mean, it couldn't happen at a better time. And people are, you know, very pleased. And about this. And it really helps to justify this program too, because it's another way at getting at MTBE. You know, if you can really isomerize butylenes and get to the product that way. So, but they're doing. It's really helping us pull our business through for the last couple of years, and you know, they project to the middle of this decade, into this decade, there'll still be plenty of opportunity for oxygenates.
You talk a lot about propylene, but MTBE requires butylene. I don't remember what you said. What were the butylene selectivities?
Right. They're running about 20 to 30% roughly.
As opposed to the 60%?
For propylene. Right. And then within that C4 product distribution, they're totally equilibrated. So you have to take another, you know, 20-some% off of that for isobutylene.
Well, if there are no other questions, let's thank Dr. Gaffney again for his Thank you for coming.
Thank you.